কনফার্ম
Yo,
করে আওয়া যাও,
আচ্ছা
কনফার্ম
ঠিক
করে
আছে।
রাতে দিবি।
আমি গেলাম, একটু গোসল করতে হবে, যাই থাক।
আমি
ভালো
চলে
থাকিস।
যাবো দোকানে।
ভাই একটু মিউট করো অফ যাও, ক্লাস শুরু করবে।
Hello, can you hear me?
হ্যালো লাউস,
Hello. Let's have our class. Before starting our class, please rename your conference name to your ID and your name, your real name. First, your student ID, then your real name. Okay. Last class, I have already told you rename your conference name to your student ID and your real name. If you rename your conference name to your student ID, it's okay. Your real name is unnecessary. If I can find your name with your student ID, please put your student ID before your real name. Real many students who don't change their conference name to their student ID. We don't wait for them. I just
ভাই যাদের যাদের
start
স্টুডেন্ট
our
আইডি নাই
class.
ওরা আইডিটা দিয়ে দাও।
Okay, let's have our class. This class, I will introduce the hardware structure of a microcontroller. As you know, microcontroller is a chip, with many pins. So first, before we learn the microcontroller, we need to know the function of the pins. Functions of the pins. You can see this is a 8051. This is a 8051. SF 8051. there is 40 pins. There are 40 pins. 40. And if we categorize pins to different types, we can see here is a P0, P0 port. Here is a P1 port, P2 port, P3 port. Every port has 8 pins. So 1, 2, 3, 4, 8 pins port. This is pins for the power source. Here is for critical. Here is for memory. Here is for memory. This is alternate function for the port P3. Port P3. Serial input port, serial output port. External interrupt 0, external interrupt 1. Time 0 external input. Time 1 timer 1 external input. Here is external data memory write stop. Here is the read stop for the external data memory. Next, I introduce the memory. The 8089C51 has 128 bytes of on-chip RAM, plus a number of SFRs. SFRs means special function register. Special function register. Special function register are used by a chip itself. Here is internal memory. Internal memory structure. No 128 bytes. Up 128 bytes. It's a special function register used by the microcontroller. It's 0 to 7F. 7F is used by users. No 128 bytes of internal RAM. The area can be divided into 3 parts. Part 1, register area. There are 4 banks of register. 4 banks. Register banks. There are 4 register banks. From 0 to 1F. From 0 to 1F. Part 2, bit addressable area. Part 3, user RAM area. This part is used by users. So when we made a program, if we want to use some RAM, we need to use this part. It's the structure of memory. Here is bank 0, bank 0 registered bank, bank 0 registered bank. Registered bank includes R0 to R7 register, R0 to R7 register. This is bank 0, bank 1, bank 2, bank 3, bank 3. This is here is for register bank, register bank. Here is for from 0H to FH, to FH. Is for bit addressable area, bit addressable area. From 30H to 7FH, 7H, as this part is for user, for user. Register area, register bank 0, register bank 0123, 0123. The address in this area are 0H through 1FH. The first 32, first 32 bytes, 32 bytes. This area is grouped into 4 banks, 4 banks of 8 registers, registers. R0 to R7, R0 to 7. How do we decide which register bank to use? We use 2 bits. Use 2 bits in PSW, PSW, program state words. There is 2 bits in program state words are used for selecting which register bank, select which register bank is in use. RS1 and RS0, and RS0. When we power on the microcontroller 8051, the default is register bank 0, register bank 0. This is no more efficacious use of code space since register instructions are short than instructions that are used direct addressing. Reset initialize the stack point, stack some special memory for interrupt, some special memory for interrupt or something to save, save data, save data. The default stack point is 07H, L7H. So in fact, the state began from 0HH. But 0HH to 1FH is a register area that will be used in program. The bank 0, bank 0 to 1, bank 0 to bank 3, bank 0, bank 3. This is the default default stack is the same with the bank 1, 2, bank 1, 2, 3. So if you use bank 1, 2, or 3, you need to change the default stack point to another address, another address. From here we can see 30H to 7FH is for user RAM area. We can select some memory for the stack. Sometimes we set that area in 30H to 7FH. Just like here. Just like here. Here is the bit addressable area. Bit addressable. Every register, every address, batch address has 8 bit address. Bit address. Here is a byte address. Here is a byte address. Here is a bit address. Bit address start from 0H to 7FH. This is the byte address from 0H to FH. Just like here, you can see here. This is 20H. This is 2FH. To FH. These bits can be addressable in two ways. Bit address, or byte address. Use the like the byte address points the bits. Point the bit. Here is the bit address 28 bit address for 25H.0. Here is 0.0, 1, 2, 3, 4, 5, 6, 7. Here, this address, bit address is 2DH, or you can just use 25H.5. Next, I introduce the user RAM area. User RAM area, there are 80 bytes. The address in this area are 30H through 7FH. Stack always are arranged in this area. If the stack pointer has been initialized to this area, enough bytes should be left aside to prevent SP data destruction. If you arrange the stack in this area, you need to be careful to left enough memory for your stack. The upper 100 bytes of internal RAM are used for PSW, special function register. The upper 128 bytes is only used as a SFR and can only be accessed by direct addressing. The addressing space is 80H to FH. For example, you move the 80H move to this digital number to 80H. You use this address 80H 80H. You cannot use this indirect addressing. This is wrong. This is wrong. Here, I need to know. You need to know if you put a pound. Put a pound sign. Put a pound sign before the digital. Before the number. Before the number. You mean this is just a number. You say just a number, not a address. Not a address. If you use a number just like 80H, it means this is address. This is address. Direct address. Direct addressing. Here we move the 80H to R0 register. Then we use this indirect indirect addressing to access 80H. This is wrong. This is wrong. Special function register. Special function register. There is one special function register. PC. Program counter. PC. Program counter is not addressable for the user. Is not addressable for user. Left SFRS 21. SFRS is addressable for users. For users. This is addressable SFR. SFR. This is address. S is a symbol. Mostly we just remember use the SFR. SFR. Use the symbol. Use the symbol. Some we don't remember the address. Just use the symbol. We use the A, ACC, B, PSW. Not use this address. Not using this address.
Laoshi,
What?
please, can you go back and give that statement again? I didn't really get it.
Sorry. Sorry, can you speak again?
Laoshi, I mean the other page. Can you go back to the symbol, the ACC?
Go back to.
Yeah, Laoshi. So the accumulator and the B register program status word, they are all memories.
Yes. This is a memory. This memory is used for special function. Special function register.
Okay.
You need some concepts. The memory is for the for saving data. Register is a part of a memory. Register is all the register part of the memory.
Okay.
The register is included in the RAM memory. Yeah.
Okay.
Okay. This is some bit addressable SFR. SFR bit addressable. Bit addressable. When you use when we use this SFR, SFRS, we can use the bit address, just like here. This is for P0. We can use P0.7 and P0.1 access the bit, access the bit. This is PSW, program status words, and this words, this is PSW is a register. We can access the every bits of this register. It's just like this. Use the bit address, or we use the name or symbol, the symbol of every bits. Every bits. This is the theme. This is the theme. Every bit has its meaning. As its meaning here, PSW.7 CY, CY carrying a flag, carrying flag. This is ordinary carry flag. This is for flag 0 eligible to use for general purpose. S is for the register bank. Register bank. This OV is for overflow. This P is for parity. Is for parity flag. Parity flag. When we reset the microcontroller, this is the default status for the SFRS. We can see most of them are 0, but this one stack point is 07H. Others are 0. Next, I introduce the stack operation. For saving breakpoint and scene in working subprogram and interrupt operation. Option. SP stack point indicates the address of top of the stack. We can consider the stack as a bottom. When we put something in the stack, the things we put is at the bottom. If we want to get out the something, we need get out on the top. Get out something on the top. So the SP always indicates the address of the top of stack. When we want to save something in the stack, you use the command push. Use the command or instruction. Use push. The push add 1 to SP. Add 1 to SP. Then write date to the stack. When we want to read the date from the stack, when we use pop instruction, pausing instruction, read the date and minus 1 to the SP. Reset make the SP to the 07H. 07H. We often set a stack pointer to 30H to 7H. Next, I introduce the program memory. Before I just introduced the data memory. Data memory. You need to know the difference. This is the data memory. Data memory. After that, I introduce the program memory. Program memory. Data memory is RAM. Program memory is ROM. With ROM. So we need to know the difference. The difference.
老师
Okay.
老师 are we allowed to access the RAM, or the RAM is always fixed?
Sorry.
Are we allowed to access the RAM? Are we allowed to make changes in the RAM, or the RAM is fixed? There's no need to make changes, like to access the RAM, maybe just the ROM to program.
You access the RAM.
Yeah, I'm asking if it is necessary to access the RAM.
Access the RAM with what?
Actually, you said there's RAM and there's ROM, right?
Set RAM or ROM. RAM is for the data. When we running the program, we use the RAM. But the ROM is ROM saving the program cannot be changed. Cannot be changed. The data are stored in the program memory cannot be changed. Cannot be changed.
Okay, so the data stored in the ROM cannot be changed, but the ones
the data in the program memory cannot be changed, but the data in the data memory or RAM can be accessed and changed.
Okay.
Yeah. After we reset the microcontroller, CPU begins to execution from location 0H. 0H. This is a rule you need to remember. If we start the power on, start out the microcontroller, the CPU begins the execution from location 0H, from the address 0H. Next, 05 interrupt vectors are assigned to fixed location. Fixed location. This is a fixed location. 0 is fixed for the main program. 0 is 5. 5 address is fixed location for the interrupt. The interrupt causes the CPU to jump to the related location where it has no conditional jump. No condition jump. Instruction pointed to service routing. Service routing. Here is the fixed location for the interrupt. Serial port interrupt. Timer counter 1 interrupt. External interrupt 1. Timer counter 0 interrupt. External interrupt 0. From the address 0003H to 0AH. This is for external interrupt 0. And this is for timer 0. We can see from here 000H for the main program. 03H is for extra interrupt 0. 0B is for time 0. 13H is for interrupt 1, external interrupt 1. 1B is for time 1 interrupt. 23H is for serial port interrupt. This address is fixed. This address is fixed for the purpose. This is we need to just remember this address for the internal program memory. Here is 4 ports bidirectional I/O ports. Bidirectional I/O ports. When we make program, we use the port 0 to 3 to interactive with the external device. Each port consists of internal CPU bus, a data output range, twice data input buffer, and MUX multiplexer, data output driver, and control circuit, This structure of port 0 to 3, port 0 to 3. This is a port 0 bit, read range, write to range, bus, read pin, address and date. This is for the VCC, power source, Here is for port 3. Here is for port 2. Here is port 3. We can see from these 4 figures, there is a little different. There is a little different between port 4 and port 1 to port 3. Here we can see a little difference. There is a resistor. There is a resistor here for the port 1, port 3, and port 2. There is a resistor. But there is no resistor at port 0, So when we use the port 0, sometimes we need to add resistor for the port 0, Port 0
Can you please
has
go back? Laushe, what's the difference between port 2-bit and port 3-bit? Because both has the resistor.
Port 2 and port 3.
Yeah, Laushe.
Port 3 and port 2 and port 3 is the same with port 1. Here, port 1, port 2, port 3, they are the same. They all have the pull up resistor. pull up resistor. But maybe there is a different function for the port, different function for the port. Here you can see this is a different function. Here is a different alternative output function, but this is not important. I want to see, you need to know that difference between the port 0 to port 1 to 3. There is a pull-up resistor in the port 1 to 3, but there is no pull-up resistor in port 0. So when we use port 0, we need add a pull-up resistor. Pull-up resistor. It has no internal pull-up resistor. So P0 pins that are being used as output pins are open drain. In this case, external pull-ups and VCC must be connected to the P0 point, just like this. This is resistors. We call the pull-up resistors. Port 1, 2, 3 have internal pull-up resistors, so the pins is pulled high by the internal pull-up resistors, but can be pulled low by an external source. To be used as an input, the port bit latch must contain a 1, which turns off the output driver FET. So port 1, 2, 3 have fixed internal pull-ups. They are sometimes called quasi bidirection ports. Port 0 is considered truly bidirectional because it flows when configured as an input. After reset, one writes to all ports latch. When we write 1 to output pins of port 1, this signal is flow like this. So write 1, so the data can be the signal can flow to the outside, can flow to outside. This is the same. If we write 0, next, I introduce the operation of the port 0, 1, 2, 3. Similar to the port 1, we can use as the same. Next, clock circuit and timing. Circuit and timing. What's the timing? the time coordination the time coordination among signals in executing instruction timing. What's a clock circuit to produce a timing signal for running a microcontroller. Clock circuit on-chip oscillator, or MCS51 microcontrollers have an on-chip oscillator which can be used as the clock source for the CPU. Using an on-chip oscillator to connect a crystal or ceramic resonator between the XTAL1 and XTAL2 pins and the capacitors to ground. We can use this like this. We can use the oscillator on-chip oscillator. Sometimes this circuit is default. So when we design the circuit, sometimes we just ignore this circuit because this is default for the microcontroller. The internal clock generator produces the sequence of states and that makes up the microcontroller clock signal, ALE signal, and the machine cycle. How to drive the clock with an external oscillator? Applying to the system that includes a multi-microcontroller and synchronize the clock signal among the microcontrollers. If we use many microcontroller, we need to use external oscillator to synchronize the signal. Synchronize the signal. Timing units. 4 types of timing units: phase, state, machine cycle, instruction cycle. Pulse and state. P phase. Oscillator period. S is a clock cycle. Two oscillator period, we get one clock cycle. Here is a machine cycle. One machine cycle is equal to 6 this clock cycle. 12 oscillator 12 oscillator period or oscillator cycle. Okay. this 12, 112. We need to remember this relation. If oscillate cycle is 12 mH is m hertz, then the time machine cycle is 12 divided 12 is equal to 1. This is the oscillating cycle. We get the 2 mu s 2 mu s machine time machine time. Instruction cycle the maximum timing unit the time to execute one instruction expressed by the number of machine cycles. According to different instruction, one IC instruction cycle can be included 1, 2, 3, 4 machine cycles. 1 machine cycles. Next, introduce the working modes. Reset mode, idle mode, and the power down mode. Idle mode, power reducing mode. Power down mode, power reducing mode. Reset mode. Reset is the initialize operation of a microcontroller. The reset pin is the RS pin, which is the input Smith trigger. As reset is accomplished by holding the RST pin high for at least 2 machine cycles. 24 isolate periods by reset cycles while the oscillator is running. After reset, PC the program counter is equal to 0h. Microcontroller executes the program from 0h. When the program goes wrong, reset operation can let the microcontroller get out of trouble. Reset operation affects the content of some SFRs. After reset, most of SFRs become 0. But the stack point is become 07H. Idle mode. Set P counts 0.0 will let microcontroller go into idle mode. The internal clock signal is graded off to the CPU, but not to interrupt timer and the serial port functions. The CPU state is preserved entirely. This special function register maintain their data. The port pins also hold their original logical status. ALE, PSEN pins hold high. This is when we set the idle mode. There is 2 ways to terminate the idle. enable interrupt, hardware reset, hardware reset. Both of them will cause pcons point 0 to be cleared by hardware. Jump out from the idle model, from the idle model. Power down model, power down model. When the sense pcon point 1, will let microcontroller go into this model. The on-chip oscillator stops with the clock frozen. All functions are stopped, but the on-chip RAM and SFR are held. The port pins also hold their original logical states by their respective SFR. ALE, PSEN pins hold no. The only way to terminate this model is hardware reset. In this model, VCC can be reduced to no as 2 voltage. However, VCC must be restored to its normal operating level before exacting power down model. VCC must not be reduced before this model is invoked. Research that terminates this model also frees the oscillators.
Laoshi,
Okay.
Laoshi, can you send us this PPT? And also, it's time for break.
What break?
Yeah, it's already 3. The break is at 2:50. Laoshi,
Hello.
hello, Laoshi. I mean, can you send this PPT to our group page?
I have sent the PPT last time. Okay, I send it again. Okay.
Okay.
Okay,
Jel,
I send you again.
Jel, can you hear me?
Yeah.
Yeah.
Laushi, if you give the break 10 minutes later, then it will be better. Because today is Friday and we have prayer. So after 10 minutes, it will be prayer time. So
Okay.
can you extend the class for 10 more minutes and then give the break?
It's okay.
You want to have a break? Okay.
Yeah, Laoshi,
Okay.
but not now. Not now. After 10
Not
minutes.
now, 10 minutes later.
10 minutes later.
Yeah, Laushi.
Okay. We have a initial. We can finish this PPT.
Okay.
Okay. It's power down model. Power down model. Power down model and the idle model. Idle model is for the power saving. Power saving. If we don't have enough power for the microcontroller, we can set to idle model. Reset model just jump out from the trouble, get out of the trouble, or just start from zero edge address. Okay, let's have a break. Okay, everyone, let's have a break.
Oh, Laoshi. Okay.
Okay, you use anything you can.
They wanted a break after 10 minutes so they could have a prayer, but
because I have finished this section. You need you can have a rest. Have a rest. Okay.
okay. Razak, is that okay?
Okay, Lavshi.
Okay.
Okay, okay.
Yeah, Jail, it's okay.
Okay, okay.
সাইদুর জামান তোমার মাইক মিউট করো।
Now, thank you for the PPT. Received.
Hello, everyone. Let's start
Hello, Laushi.
our
Okay.
new session. New session.
Laushi,
Okay.
yes, before go to another chapter, I have some questions.
Okay.
Laushi, about page 27.
Page 27.
Yes, chapter 2.
Page 27. Okay.
Yes, Laushi. Can you open your PPT, please? Yes, Laushi. Yeah, he has 2.3 parallel input-output ports. The structure of port 0 to port 3. Laushi, I want to know how they work, in which condition they can be considered as input or output.
You want to know how to action as input or output?
Yes, of course.
You want to know how to know work as input or output. This 4 figure just give you some symbol for this for the function of the port for the function of the port. As the port 0, this is the pin of the port 0. Here is the inside. Here is the inside of the chip. Inside of the chip. When we want to read this status on the P0, here is read range, read from this register. This P0 point X range, read range. When the signal come on the point 0, the signal is come to here. It's come to here. And knocked here. Knocked here. Then if we give the read instruction, the data will be transferred from here to the read. If we want to write to the range, we write it to here. Write from this. Write to the range. Then the data is flow. The signal is flow to here. Flow to here. There is a multiplexer. This is a multiplexer. We can change the data from date from the data to the address here is address address and yeah
What's the use of this multiplex here?
multiplex multiplex because the P0 can output the digital or data output data or address we can change the change to
Signal.
data or address with this multiplex yeah.
So they can change one signal to different direction, right? 2 or 3 direction.
No, this can change the data from signal from data to address to this, which means we can output the data from the P0 or output address from the P0.
Okay.
For the port 0, port 2, and port 3, we can just output the data. We cannot output the address.
Yeah.
These 4 figures are just tell us the there's some difference in this between the ports but sometimes I think we need to remember the function of the P0 to P3. The P0 can output address and data, no pull-up resistance. The P1, P2, and P3 port 3 only can only output data and with pull-up resistor.
Laoshi.
Okay.
Example, Laoshi, port 0. It can be input or output. I want to know in which condition, Laoshi. There is no condition to be one.
You want to any condition this port 1 can be output or input.
Example, port 0. Yes, I'm talking about port 0.
Before we can use the input, we need write 1 to port 1 and I give you see the use as an input the port bit range must contain 1 which turn off the output driver so if you want to use the port as input you need write 1 to the port write 1 to the port.
Okay.
So Laoshi, what's the main difference between these port 0, 1, 2, 3?
Different.
Yeah.
The port 1, port 2, port 3 we think they are the same, but the port 3 have the
And 0.
alternative function. Has the alternative function.
Okay. So Laushi, can you explain this 4 figure one by one? Then maybe we will understand more clearly.
I think there's no different, many different about the figure. You want to
But
know?
those figures are different from one to another, you see.
Yeah, I
So,
can see you some there's some difference. You can see.
yeah. Can you please explain one by one this figure? Then maybe it will be very clear to us.
Okay. This is port 0. Here is a multiplex. But the port 1, 2, 3. There is different.
No multiplex.
Here.
Have multiplex.
This has a multiplex. This has a multiplex. What's multiplex?
Yeah.
Yeah.
Port 2, yeah.
Multiplex. When we are interactive with the external device, the P0 and P2 can output the data and the
date.
address. And P0 is no H address. P2 is higher H address, So they have the multiplex. Port 1, 2, 3, they all have the pull up resist. This is common. This is common between them. Yeah. But there is no pull up resist H port 0. So if you want to use port 0, you need add pull up resistors. And this is different between one with and one port 0 to the 1, 2, 3. This is different. Here is different.
Fine.
When we use the port 1, 2, 3 as a common port, they are the same. We use just use the common port output and input the data. Port 1, 2, 3 is the same. Are the same. But the port 3 has an alternative function. This is a different difference between 1, 2, 3. 1, 2, 3. Port 3 has an alternative function, but the port 1 and port 2 they don't have alternative function. When we use address, the port 0 and the port 2, they have the common. They have the common. Port 0 can output lower H address. Port 2 can output a higher H address. This is a connection between port 0 and port 2. Port 0 and port 2. This main difference between these 4 figures. Actually, you see.
Yeah, Laushi, what about port 1 and port 3. Here we can see here one is NAND gate, but in port 1 there is no NAND gate. Can you see it in the middle? Alternate output function. Here is a NAND gate.
Yeah, Laoshi is a little bit complicated.
Gate.
Yeah, you can see here in the middle. It's a NAND gate, right? Or NOR gate, even I forget.
There's no way you can show it, Laoshi, because it's online. You cannot point fingers, so it's hard.
I don't see any NAND gates.
Laoshi, in port 3, the last
Port
one.
3.
Yeah, the last one in the middle. It's a NAND gate or NOR gate. Which gate is that one?
Oh, you said this gate.
Yeah.
Oh, this gate can change the function to the alternate function. Alternate function.
Yeah, but in port 1 there is no NAND gate, right? So
yeah, this
so
port one.
it should be
Port 1 is
the output should be different.
only can use the output that there's only one function. This
one?
port 3 has two functions. Port 1 only only has one function. One function.
One function, right?
Yeah.
Okay.
Port 3 port 1 has one function. Port 3 has two functions.
So Laoshi, what is the output for port 1 and port 3?
Output.
Yeah.
If we use port 1 and port 3 as a output or input function, we can see this is the same. This is same.
Yeah.
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 But
what I'm talking about.
but the port 3 has an alternative function. So when we change to the alternative function, we use actually we use this. Use this. Yeah.
Okay, Laoshi.
Okay. Any questions? Okay. Let's start our new session. Next, I introduce the instruction systems. Instruction systems. Instruction systems. We use the instruction to control the microcontroller. Microcontroller. The main concept about instruction formats, addressing model, and instruction. Instruction formats and addressing modes are a symbol language. We use a symbol language to control the microcontroller. Symbol language. A symbol, a computer program used to assemble a symbol. When we make a program, we get the source program. We use assembler, change the source program to object program. So we get the object program. The program can be executed. Can be executed. Here is source code. Here is machine code. Machine code. Machine code consists of 1, 0. So they are harder to remember. So we use assembly language, symbolic language to make a program. If we want to use assembly language, we need to remember instruction sets. Instruction sets. Instruction format. Instruction is equal to opcode and operand. Opcode, operand. Opcode and operand. Opcode plus destination operand and source operand. Operand. Instructions types. 1 byte instruction include opcode and operand. 2 bytes instruction. First byte is opcode. Second byte is operand. Operand. 3 bytes instruction. The first byte is opcode. The second and the third byte are operand. Operand.
Laushi,
Hmm?
please, can you go back one step? What's the difference between the opcode and the operand?
Opcode just like the command. Command. The operand just the you can the command tell the source and do something or move some value to the destination. And this opcode like command. This like the target. This like the target.
So Laushi, operand is the destination.
Operand not the destination. Operand is the target, the opcode. Opcode. Operand sometimes maybe only there's one operand or 2 operand. Operand or 2 operand. If there is 2 operand, maybe the first is destination. The second is source. Is source.
Oh, okay, okay.
Addressing model. Addressing model. Addressing how to get the location of operand. Operand. Addressing model are 7 types. 7 types. 1 register addressing. 2 direct addressing. 3 register indirect addressing. Immediate constants addressing. Indexed addressing. Boolean addressing. Relative addressing. Relative addressing for getting the jumping destination. There's 7 types of addressing model. Addressing models. First, register addressing. Operand and denoted by register. By register. For example, this is a opcode. This is operand. Operand. First operand is the destination, and second operand is a source. Here we use R0. R0 is a register. Register. So we call this register addressing. Register addressing. This instruction and the meaning is move value in R0 to A register. A is a register.
I thought you said R is the register.
R0 is the register.
A is the what?
What?
A, the value A. What is the value? You said move
A.
A to
A is a
RO.
register. A is a special function register. A, or sometimes we write A or ACC.
Okay.
A or ACC is okay.
Okay.
We just write A. A is a register. Register. Addressing range. Addressing range. Generally, general register. Four banks. For banks register 032 register, we can use the register addressing some special function register A, B, DPTR, etc. etc. This is some special function register. Special functions register. This is register
So all of
addressing.
these are operand, right? This A, B, D, P, T, R.
Yeah, this is a special function register. We can open the last class Schneider PPT. You can wait. Yeah, last class I told you held register, special function register. You can see.
Yeah.
CC is A, ACC is A, it is B, PSW, DPTR is all this special function register.
So, Laoshi, do we have to memorize the special function registers?
Memory this.
No, do we have
function.
to memorize?
How to memory?
No. Do we have to like remember all of them?
Oh, if you want to use the microcontroller, you need remember this symbol. Use with the remember the symbol of the special function register. If we use the register to control the microcontroller.
Okay,
if we want to control microcontroller, which means we just write the command or something to the register.
Okay.
This register addressing. Register addressing. Direct addressing. Direct addressing. Direct addressing, which means we just use the address. Use the address as the operand. Use the address as operand. It's move the value. It's address 3AH. Move to A. Move to A. This is a direct addressing. Direct addressing. Addressing range. Addressing range. Lower 128 bytes of RAM, internal RAM, and SFR, special function register. It's direct addressing. Direct addressing. Register indirect addressing. Indirect addressing. operand special files registered to contain operand address with the prefix 8 prefix 8, which means address register of 8 address RI address register 16 bit address DPTR we can use it's put 8 before the register we can use it as a indirect addressing just like this we can get the value in the R0 as a address, then we can read the address and get the data, then move to A. This is the meaning of this language. Move A, comma 8 R0 R0. If you see an H before the register, you know there is a value. Address value in the register. So you want to get the data value, you need read the address in the register. Addressing range no 128 bytes of RAM or 64 KB of external RAM. This is internal RAM. This is external RAM.
So Laushi, when we will see this at the rate, that means it's a indirect addressing, right? Register indirect addressing.
Indirect addressing for what?
Yeah, this sign, this @ sign. So that means
yeah.
it's an
You mean this sign?
Yeah.
If we put sign 8 before a register, means indirect addressing.
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 Yeah. Okay.
Immediate constant addressing. Immediate constant addressing. This is constants. Which means if we put a pound before value, this is a value, just a value, not a address, just a value. Move this value 3A to A register. Move this value to DPTR which means this is a value not addressing. It's constant.
And also this MOV, it's a opcode, right?
MOV is a opcode.
Opcode.
This is operand. This operand.
Yeah, DPTR is the operand, and MOV is the opcode, right?
Yeah.
Okay.
DPTR is a destination register.
So sometime it should be destination and sometime it should be source. So when we will understand what was exactly that one?
If we use the if there are 3-byte instruction, first is opcode, and second and third are operands. If the second is a destination operand, the third is a source operand.
Yeah. So
if we have 2-bytes instruction, first is opcode, the second is destination
operand.
and source operand.
So
The
I'll
second
show
is source and destination.
Laoshi. Laoshi. It means that the opcode direction, destination operand and source operand is the format. Yeah, sorry, format, right? So when we are writing the code, we need to follow this format.
This is format, yeah.
So we need to follow
it's a
this format.
serial. That's okay. Yeah.
The destination before the source.
Okay.
Yeah. The destination before the source. There is a comma here.
But Laoshi, here is 2-byte instruction. The first one is opcode and the second one is operand. But the second one, what kind of operand is that? It's a destination operand or source operand? So how we will understand?
If there is 2-bytes instruction, the second byte is operand, and it is destination and source, which means you can operate on the operand and save your result to the operand.
Okay.
Okay, Lord.
Yeah. Next, I introduce the indexed addressing. Program memory can only be accessed by this model. Program memory, which means ROM. Designed for reading looked up table. Designed for reading looked up tables in program memory or executing unconditional jumps. 16 bits base register, DPTR or PC, points to the base address of the table, and A is set up with the table entrance number, which means DPTR or PC point to the start address of table and A is offset, and A is offset. If A is 0, which means we just jump to the first place of the table. If A is 1, we jump to the second place of the table. The 16-bit address in ROM is formed by adding the A data to the base points. Only 3 instructions. Move C A comma A 8A plus DPTR as A plus PC, or just JMP. JMP, which means jump. This is a instruction. Jump. This means we can look up the table and get the code move to A. Move to A. This is from the PC and add the offset get the value and move to A. Move to A. This is jump JMP jump to this address. Jump to this address.
Laoshi, please can you go over it again? I didn't understand.
Sorry.
Can you go over, like, can you explain it again? I didn't understand. Why is there...
you want to explain again?
Yes, please.
Okay. This index addressing just use as reading look up tables in program memory or additional jump. So when we use this command or instruction, the three instruction, we can give the address of the table to DPTR PC or PC and add an offset to the table. So we can look up the table and find the value in the table. And give this this stage to A to A.
So Laoshi, so if we add the operand should have C. Sorry, the opcode should have a C. So move plus C.
Move plus C.
Yeah, there's a C attached to the move.
Oh, you mean this move C?
Yeah.
This move is different from move C. Move C is just for the ROM memory, program memory, not for the data memory. This move C is for the program memory, not for the data memory.
I get it. So Laoshi, so when we use move, we are using it to retrieve from the RAM. When we use move C from the ROM, right?
Yeah. Move is for the RAM. Move C is for the ROM. Yeah.
But Laoshi, when we find the value of A in the DPTR, because of the @ sign, it becomes it becomes what's the name? The @ sign. You said when we have the @ sign, which addressing is that?
DPTR or PC is point to the address of the table, and this A is point to the offset of the table So A plus DPTR, we can get the actual value in the table. Yeah.
Okay.
So from this address, we can get the code, the program. So move this code to A. Move this code to A.
Okay, Laoshi.
Yeah. Next Boolean addressing Boolean addressing range bit addressable area in internal RAM just one bit bit address bit address serial address 20H to 2FH and bit address 0 to 7FH serial address which means this is for serial every serial has 8 bits 8 bits. So if we want to access the bit H the 20H, we just use 20H.0 to 7 or just use bit address 0 to 7H to 7H. Just like this. This is a serial address. We can get the bit address. This just use the bit address. Bit address. Bit address in SFRS. There is 4 ways to specify the addressing bit. One is use PSW.5, just the SFR symbol at bit. 2 bit address 2 bit address 3 serial address plus bit serial address plus bit 4 just the bit name bit name. First under the fourth use the name second and third use the address this is bit address is the serial address. This use the serial name. This use the bit name bit name. This is these are these are 4 ways to specify the addressing bit. Relative addressing used for getting the jump destination address of PC in jump instruction destination address is equal to PC add plus relative addressing. PC is equal to address plus bit number of jump instruction. Relative is equal to 8 bit relative offset bits Next